my name is Trinity Alvarez. It's currently July 18th, 2020, and today we'll be discussing my Unit 2 case connections. I chose case 3 and 4, so we'll be discussing case 3 and 4 today. Starting with case 3, we are starting out with this cute little dude. He's a 5-year-old boy who's brought to the pediatrician's office for his annual visit. His mother reports that he's been a sickly infant, often appearing drowsy. She's also concerned that he's been drinking a lot. And then frequently urinating. They also do some blood work at his visit, and his serum insulin levels are shown to be quite lower than the baseline, even after a glucose load. So I thought the most appropriate diagnosis for this kid was diabetes, particularly type 1 diabetes rather than type 2 diabetes, because type 1 diabetes often has an early childhood onset rather than a more gradual onset later in life. Making it the more appropriate diagnosis. So normally when we eat, the components of our food are converted into glucose, and then glucose enters the bloodstream and travels throughout the body. One of the stops it makes along the way is the liver, where the glucose is sensed by the pancreas. Once the increased levels of glucose are sensed by the pancreas, it releases insulin. Insulin is mainly responsible for decreasing blood glucose levels by making glucose accessible to the rest of the body or storing it in the liver. If glucose is high, then insulin is generally high too, and if glucose is low, then the pancreas releases glucagon in order to achieve homeostasis of the blood. So I kind of drew this here. So on this side we have insulin, and it means low blood glucose, and on this side we have glucagon, and generally means high blood glucose. So in the case of type 1 diabetes, his insulin doesn't work, so this is what's going on in his body. It's just not there, but glucagon is still normal. So it doesn't work because the body has very little or lacks insulin completely. This is different than type 2 diabetes. In this case, the body has grown a resistance to insulin rather than it not being there in the first place. And in type 1 diabetes, it elicits an autoimmune response where insulin cells are destroyed by the body's own immune system. So since the increase of blood glucose is never acknowledged, his blood glucose levels would most likely be above the normal range because the body just isn't processing that blood glucose is high. So the body basically thinks that it's starving itself, when really there's a lot of glucose there. It just can't access it. So since the increase of blood glucose is never acknowledged, blood glucose levels will most likely be above the normal range. With the absence of insulin, the body tries to dilute the increased blood glucose levels using water from the cells, and since water is leaving the cells, this could contribute to the patient's constant thirst and frequent urination. Since the glucose has to find a way to escape since it's not being used, the urine is now the most accessible tract. The patient's sickly and drowsy appearance is likely caused by the body's inability to use glucose as energy, so it's trying to find an alternate source of energy in the rest of the body. And since glucose is the main way that we get energy, he's probably very tired because the body just can't keep up without glucose. I thought of it as an analogy for it, and it's kind of like if you have all these houses that are getting a water supply in a normal body, and then all of a sudden one of them gets clogged. The water is still flowing down the street, but it's not getting to that one house. So insulin is like a drain snake for the body, and allows glucose to be accessible for the rest of the body. I thought two of the regulatory enzymes in the patient's current condition are glucose 6-phosphatase and pyruvate carboxylase in the liver. Glucose 6-phosphatase is primarily found in the liver and is mainly responsible for dephosphorylating glucose 6-phosphate into glucose, so the free glucose can be released from the liver. Glucose 6-phosphatase is primarily regulated by the concentration of glucose 6-phosphate, and studies have shown that the concentration of glucose 6-phosphate is elevated in individuals with diabetes, so glucose 6-phosphatase would be active. The other enzyme is pyruvate carboxylase, and that's responsible for catalyzing the carboxylation from pyruvate into oxaloacetate, and since it's repressed by insulin, it would most likely be active in the patient's current condition because the patient biochemically appears to be in the fasting state even though there's an excess of glucose in his blood. Next, we're going to talk about case 4, and case 4 regards Jane Doe, this very previously healthy 2-month-old female who initially presented with jittery spells after breastfeeding. She's been sleeping for no more than 2 hours at a time, and then having symptoms of hypoglycemia, and then upon physical exam she has a large liver, and she cannot maintain glucose blood levels within normal range while she's fasting. So I thought that the answer would be glycogen storage disease, but first I'm going to talk about why I didn't think it was the other ones. So I didn't think she was suffering from hereditary fructose intolerance because hereditary fructose intolerance affects the enzyme aldolase B and the ability to break down fructose. Since she's only had a diet of breast milk since she was born, and breast milk contains lactose, I didn't think there was enough evidence to support looking further into this disorder. I also didn't think she was suffering from glucose 6-phosphate dehydrogenase deficiency because the disorder exclusively almost affects males, and it affects how the red blood cells carry oxygen from the lungs to the rest of the body, and it causes them to break down prematurely. And since she's having trouble maintaining blood glucose levels, I thought there wasn't enough evidence to look into that disease either. Which brings me down to galactosemia or glycogen storage disease. I didn't think it was galactosemia though because galactosemia impairs the body's ability to process and use galactose. Galactose is present in all milk because it's made of lactose and glucose. However, the patient's symptoms didn't really align with those of classic galactosemia. Classic galactosemia included loss of appetite, vomiting, jaundice, weight loss, and the patient initially presented with jittery spells, hypoglycemia, and an enlarged liver. And since the patient can regulate galactose in the fed state, I didn't think it was this disease, since she's most likely able to process it if she can do it in the fed state, just not the fasting state. So the reason I thought that it was glycogen storage disease, which is the body's inability to metabolize glycogen into glucose, is due to a mutation of glucose 6-phosphate in the liver. Normally during the fasting state, when our blood glucose levels are decreased, the pancreas signals to the liver to break down glucagon into glucose to help increase those levels again. This causes the release of glucose 6-phosphate from glycogen, and then the liver contains the enzyme glucose 6-phosphatase, which removes the phosphate from glucose, and then it is able to be entered into the bloodstream. Similarly, the adrenal gland also uses epinephrine to signal the muscle cells to break down glycogen into glucose. But skeletal muscles can use glucose 6-phosphate as is for energy, and they don't need to cleave the phosphate to use it. So this just means that the muscle cells can only use it for themselves, and they can't help release it to the rest of the body. But in the case of glycogen storage disease, glucose 6-phosphatase is mutated, so the phosphates can't be cleaved off of the glucose, and it cannot be broken down and released from the liver. So this results in an excess of glycogen, which is probably the cause of her enlarged liver, as shown by the patient's physical exam. And since the patient initially presented with jittery spells hours after feeding, it was a sign of hypoglycemia, which was later confirmed by lab results. Epinephrine likely only caused an increase in the patient's blood galactate levels, since it signals a signaling cascade in skeletal muscles, which produce lactate rather than glucose in their pathway. So those are the main reasons I thought it was glycogen storage disease, or the inability to use glycogen rather than any of the other diseases. I hope you enjoyed listening to me about my Unit 2 case connections, case 3 and 4.